It was thought by philosophers of ancient Greece that light and vision were the same, that light originated in the eye. But why then could we not see in the dark? Isaac Newton suggested light was a stream of small particles which could cross the vacuum of space as tiny projectiles. 19th century physicists proposed light as a wave of energy and clung to the Aristotelian concept that the universe contained an ether which transmitted the waves. But light casts well-defined shadows. It must be corpuscular. A wave would bend around corners. No, light is like the sea. Its waves interfere with each other, producing bands of light.
Light was first thought to be a particle. Later it was thought to be a wave, but now we realize that not only light but all matter actually shows both a wave-like characteristic and a particle-like characteristic.
Many people like to think of things they can't see directly in terms of things they see every day. For example, physicists sometimes think of atoms in a gas as a bunch of particles bouncing off each other. In some ways, light also behaves as particles in a train. However, in other ways, it behaves more like a bunch of waves. In actual fact, light is neither particles nor waves as we know them, but rather is something which shows some of the properties of each.
Light shows its particle-like characteristics during the processes of emission and absorption, and shows its wave-like character mostly during transmission.
What we call light is a very narrow portion of the entire electromagnetic spectrum to which the eye is sensitive. It encompasses a range from 380 nanometers to 760 nanometers. And this ranges from the violet through the blue, the green, the yellow, orange, and on to the red.
In a superficial way, we can see that light travels in straight lines. The sun's rays cast sharp, well-defined shadows.
This can be shown by using a pinhole camera, a pinhole for the light to go through from a luminous source, downward rays emanating from the top of the bulb and upward rays emitted from its base, pass through a pinhole forming an inverted image of the light bulb. Only rays that travel in straight lines could form an inverted image.
In a thunderstorm, you see the flash of lightning, and a few seconds later you hear the clap. The light gets to you almost instantly, and it takes a little while for the sound to get there, because it only travels 1,100 feet per second. The light travels 186,000 miles per second. That's a big number. As a matter of fact, it appears to be one of the universal numbers in the astronomical world. It's such a big number that they think it cannot be exceeded. It's also a very useful number in dealing with the tremendous distances involved in our universe. Some of the stars are so far away that you can't measure them in miles. You'd have so many zeros you couldn't write them on the blackboard. A light year is the distance a light ray would travel in a year. That's 186,000 miles per second times the number of seconds in a year. When you multiply that out, it comes to 6 trillion miles. That's a convenient unit for the astronomers to use because the distances in the universe are so great.
Light reflected from a person's face is transmitted to our eye, and our brain interprets it as a woman's face. If light is reflected again with no distortion, without other information, we would believe we were seeing the real face. The reflected image of a mirror fools us into believing that the person is located at a point beyond the mirror.
When light strikes a surface, three things can happen. It can be absorbed by the surface, it can be transmitted by the surface, or it can be reflected from the surface. The law of reflection states the angle of incidence of light is equal to the angle of reflected light. something like the way a billiard ball leaves the edge of the table when it strikes the rubber cushion. This angle of reflected light is most obvious from a shiny surface. On the other hand, a diffuse surface tends to scatter the light that leaves it.
Curved mirrors can be designed to reflect light in an orderly and specific fashion.
We can use a concave mirror to focus light in much the same manner that we used the convex lens. Takes parallel light and brings it to a point focus.
A flat mirror produces an image equal in size to the object in front of it. A convex mirror reduces the size of the image, and so you can see yourself from head to toe in a Christmas tree ball. A concave mirror, as you see in a funny house, distorts your image so that it can make you look taller or fatter or wider. This is because the curved mirrors don't give you the same size image as the object.
When light changes speed, it bends. This is known as refraction and occurs when light passes from one optical density through another. The degree of bending is described by the index of refraction for a given substance.
A mirage is caused by the bending of light rays as they pass through layers of hot air near the ground. When we look through a substance having an optical density greater than that of air, our eyes deceive us. We've been accustomed to seeing through air, and objects appear distorted in other transparent mediums. As light enters water, refraction takes place, and its velocity is slowed to 140,000 miles per second. In a diamond, refraction is even greater, and the velocity of light is slowed to 77,000 miles per second. Light is trapped within the substance because the diamond's facets are cut at angles that reflect most of the light internally. When light passes through a glass lens, it is bent twice, as it enters and as it leaves.
With a convex lens, light rays are focused to a point, like the lens you use to burn a hole in a piece of paper. Concave lenses spread parallel rays apart, like a garden hose.
Using a convex lens and a ground glass to focus upon, and an object, a luminous object behind me, by moving the lens back and forth, we go in and out of focus. This is because the refraction of light as it passes through the lens focuses the light at a point, the focal length of the lens.
The lens of a portrait camera bends light to a focus, inverting the image on the camera's ground glass. Lenses of varying combinations and resolving powers allow us to see our universe more clearly.
Refraction is the bending of a light ray by a prism. Dispersion refers to the fact that different wavelengths of light are bent in different degrees. Blue light is bent the most, and red light is bent the least, so that you come out with a spectrum of light throughout this dispersion angle. The problem with a lens is that the same thing happens. In a simple lens, parallel rays are brought to a point, but the blue rays, being bent most, come to focus here, and red rays, being bent less, come to a focus here, so that wherever the image is formed, you get chromatic aberration, or a color fringe on the edge of the image. To correct that, you have to have a very complicated set of compound lenses, so that the lens in your camera, for example, actually consists of 3 or 4 different layers of glass of different indices of refraction, so that they bring everything to a focus at exactly one point.
The diamond's ability to disperse light is unequaled. It spreads light into a spectacular display of color, and perhaps for this reason has been regarded as a precious gem since early times.
The wave properties of light are clearest if the light comes from a small point and is very pure in color. We call such light coherent. We can make a source of light that is coherent and millions of times stronger by using a laser. A laser is simply a light-emitting medium with mirrors on either end of it. In the case of the laser you will see, the light-emitting medium is a gas with electrical current going through it. The electrical current excites the gas atoms, and as they de-excite, they emit light. The light bounces back and forth between the mirrors and establishes a regular wave pattern. As this pattern is established, the light becomes extremely pure in color. One of the mirrors is made slightly transmitting, so that some of the light comes out of the light-emitting medium and into the open room. This is the output of the laser. This beam is extremely pure in color. That is why we can get such a powerful source of coherent light from a laser.
The phenomena of diffraction illustrates the wave nature of light. Here we have a razor blade and a wire placed in a beam of light and shadowed on a projection screen. If light traveled in straight lines, the edges of the shadows would be perfectly sharp. However, if we look closely at the shadows, we see that these edges actually have structure. In particular, a dark halo around the outside. Because light is a wave, some of the light is bent into the region of the shadow, reducing the intensity of the light outside.
Here you see an argon laser. When part of this beam is blocked by a sharp-edged object, a shadow is created which also appears to be sharp-edged from a distance. However, if you look closely, you can see that some of the light has bent around the edge of the object and spilled over into the shadow, much as water waves bend around the edge of a breakwater. We call this bending of the light waves diffraction. If you look even closer, you can see another aspect of diffraction. Immediately above the sharp edge is a series of bright and dark stripes. The light that comes near the edge gets out of step with the light that's coming further from the edge, and where it is exactly out of step, it cancels and creates a dark stripe. The patterns of light and dark get more complicated than simple stripes when the sharp edge itself is more complicated. A very good example of this is the way light diffracts around the threads in a screw.
Since light acts as a wave, interference will occur, and like water waves, light waves reinforce each other when in phase and nullify each other when out of phase.
A slightly different pattern of light and dark regions is created when light goes through a regular structure. This grading consists of alternating opaque and transparent stripes, about 200 to the inch. Light that was focused into a spot is spread by the grading into a line by diffraction. However, if you look closely, you can see that it's not really a line at all, but rather a series of tiny spots that are bright. Now you can think of these dots as being created by the light beams that go through each transparent area in the grating. These light beams mix on the screen, and in some places the waves are out of step in one beam with the waves in the other beams, such that they cancel each other just as before. This creates the dark regions. When the light beams happen to be in step, as they are in the few dots that you see, then bright regions are created. When different beams of light, such as these, combine to form a pattern of light and dark, it's called interference instead of diffraction, but the basic phenomenon is the same.
A striking pattern of color is produced when light falls on a thin film of oil.
This is caused by the interference of the rays that are reflected from the front surface of a film and the rays reflected from the back surface of the film. And so the reason you're seeing the colors of these spotlights reflected in the soap bubble change is that the thickness of the soap bubble is changing, and therefore different colors interfere as the thickness changes.
One of the most interesting modern examples of diffraction and interference is what you see in a hologram. A hologram is like a grating in that it consists of many alternating stripes of light and dark. However, when the hologram is made, the stripes are created in such a way that they bend the light to form it in exactly the same rays that the scene itself created. So that as you look through the hologram, and if you move your eye, the scene seems to change exactly as it would if you were looking at it itself.
Light normally vibrates in 3 dimensions, but certain materials can limit the light vibrations to 2 dimensions.
The vibrations of a rope are similar to light waves. The rotating portion of the rope represents unpolarized light. After passing through the first polarizer, these vibrations are only up and down. The vibrations will pass through a second polarizer when it is aligned with the first. When the second polarizer is rotated by 90 degrees, most of the vibrations are eliminated. Light waves passing through a polarizing material have only one direction of polarization. A second polarizer will pass these waves when it is aligned with the first. When the second polarizer is rotated with respect to the first, the light reduces in intensity until at 90 degrees almost no light comes through.
One way we can show that light sometimes behaves as a particle is by observing how it knocks electrons out of certain materials. When the light quantum strikes the metal, it causes an ejection of the electron if the electron energy, the binding energy of the electron, is less than the energy of the quantum. I have here a photocell. One like it is contained in this apparatus. When light strikes this photocell, it will cause an electron to be emitted from the surface of the photocell. We use a counter to count each time an electron is emitted. Bright light will cause the counter to run very rapidly. Dim light will cause it to run in a random fashion. This is because the light is acting as particles rather than waves. Individual photons of blue light are more energetic than those of red light. If I place a blue filter in the beam, light will produce photoelectrons which will cause counts on our counter. If I place the red filter in the beam, we no longer get any counts because the energy of these photons is not sufficient to knock the electrons out of the material.
Light falling on a television camera's photosensitive plate produces an electric current proportional to the brightness of the scene. The varying current is then transmitted and reproduced as a pattern of light. And the soundtrack of this motion picture is another example of the photoelectric effect. The optical soundtrack on the film varies the amount of light falling on the projector's photoelectric cell, which produces a fluctuating electric current. The current is then converted into sound. Today's scientists have the tools and techniques necessary to investigate the mysteries of light, and we are just beginning to understand its complexities. Albert Einstein, speaking of the law of nature, said, "Its harmony reveals an intelligence of such superiority that compared with it, all the systematic thinking and acting of human beings is an utterly insignificant reflection."